let's move to something like complex variable functions. And how can we solve this kind of problems? The first topic we want to talk about is how to express or how to manipulate complex variable functions. For the functions where the independent variable is a complex number rather than a real number. It might be very useful in some topics such as fractional calculus. I think we may also use this kind of functions. And how can we visualize a complex function? And then we can move on to the ideas or concept of to oppose or residues of poles. I will explain that one to you. And then I will talk about fraction, the partial fraction extension of rational functions. And then I will talk about computing closed path integrals. So suppose there is a function, such a function, complex variable function. How can we visualize it? Like for real function f, x, y, we have to use mesh grid commands to generate grids, and then on the grid we can draw three-dimensional mapping surfaces. And for complex variable functions, we can use complex grid to generate a series of grids on the xy plane. We can generate a few grids. It should be something like this. And then, based on the grid, we can easily draw the three-dimensional complex matching function using complex map function. And here is an example. Suppose we want to draw a three-dimensional mapping surface of a function like this. So to solve this problem, we first have to generate the grid, complex grid. I will explain briefly later on. And then we can calculate the original function. Remember, we have to use dot operation in the function call. And then we can call complex map function to visualize it. And I will display it first. So what's the problem?
Well, you see, this equation is in the C domain. So it doesn't matter.
C domain, yes.
So it doesn't matter which domain you're using.
Actually, it is a complex variable function, so it is in C domain, or complex domain. And we will see that if we zoom this kind of plot, we can see well, I'm not quite sure with number 50. I think if you divide the circle, 360 degrees by 50 parts to finally draw the mapping surface. And it is a unit circle in the xy axis here. If you want to have larger areas of the visualization area, then I think you have to change the function call, the syntax of function. I haven't tried it before, so for help complex grid. It may have other syntaxes, I'm not quite sure. Well, if you are not allowed to do so. There might be problems how you can enlarge the area of interest. I haven't tried it myself. let's move to the topics of poles and residues. Suppose in the X plane, in the complex plane, if we are analyzing a function, we may find that for some particular points in the function, where the function itself does not exist. For instance, this one, 1 over z, where in the origin we have 1 over 0. It can be infinity. So this kind of points are called the poles, or singular points. And the ideas of the poles is exactly the same as it is in the control systems. So the poles are the points which makes this function, the value of function do not exist. So in the function there might be some poles which makes the value of which makes the function very odd at this point, because the function values do not exist. So this is the definition of poles. And for the functional analysis, we do need some particular values for the function to fill up the infinity or not a number gaps. So we have to introduce a value to replace it. This value is referred to as residue of this point. It can be regarded as the function value of the point. So we have to define what are the residues of the functions. Suppose A is a singular point or a pole of the function. Then we can introduce a limitation like this to find another value for the function at a point that equals to A. And from this we can replace the original value of the function which does not exist. We can remove it. We can replace it with a finite number. And this number is called the residue of the function. And for single poles, I will explain the idea of single poles. For single poles, the residue of the function is defined like this. And from it can be seen that if you use Matlab, you can easily find the limit of the function and name it as the residue of the function. And for multiple poles, for instance, the function is something like this, k minus 1. So if this is a function, we say that then equals to 1 is the triple pole. And for multiple poles, we have another, this is the implementation, Matlab implementation of this function. So we can easily solve it by Matlab. And for multiple poles, if the multiplicity is n, then we have to use this formula to find the residue of the function. And there is another question is, how can we find the multiplicity n for a certain function? These are the points I want to address here. And for this kind of formula definition, we can easily implement it using Matlab command like this. So they are exactly the same. So I leave the third problem, how can we find m later, through examples. So in this way, we have